Hello everybody, welcome to today's virtual training course organised by the SGT. This is the first virtual training course we've had, and I'd like to welcome you all and to Dominio for being our first presenter. He graduated in 2016 with a degree in industrial chemistry, began his career in environmental and energy department at SSV in 2017, where he focused on emissions monitoring process and combustion optimization. In 2021, he started working in the R&D department of SSV, managing different innovative projects concerning not only energy efficiency and environmental aspects, but also other fields of glass production process. So, Dominio, over to you.
And in this presentation, in this webinar, I'm going to talk, as you can see, the combustion engineering and furnace optimization. So, how the primary techniques for NOx reduction could help the glass production process. So, first of all, let's talk about the NOx formation. And well, maybe I think you know well how the NOx formation is, but there are four main mechanisms for the NOx formation during the glass production in the glass furnace. Three of them are linked directly to the combustion, and one depends of the use of in the batch as a refining agent. In this presentation, we're going to talk mostly about the thermal, or well, the thermal ones linked to the combustion. So the main the main mechanism is the thermal NOx. So it is that at high temperature and with an excess of oxygen, NOx is generated from the breaking of air and the molecular oxygen and nitrogen. As you can see in the figures, NOx formation and its rate of formation, it depends exponentially with the temperature of the flame, and also it has a different trend with excess of O2. And the main sources of nitrogen are the combustion air, obviously, the atomizing air, for example, in oil-fired furnaces, and also the air leakage into the furnace. So, as you can see, this is another graph that shows the behavior of nitrogen for NOx formation, and it is function of the temperature. As you can see, at 2000 degrees circa, the rate of NOx formation starts to increase very quickly. So it is not important the value of the temperature of the equilibrium of the equilibrium concentration, at the rate of its formation. So there are many variables that affect the NOx generation, and the first one and the most obviously is an increase in combustion air means an increase in NOx.
Sorry, Dominio.
So there is a major concentration of O2. Please.
No, sorry, your internet is very slow. Maybe if you turn your video off and just speak, the quality will improve.
Okay. Can you hear me well now?
Yeah, I can hear you well.
Perfect. Thank you, Nigel. And so where we was? Okay. The major parameter variable that affect the NOx formation. So one parameter is the flame temperature is very important since is the one of the aspects that affect major the NOx formation is the temperature. So decreasing the flame temperature, there are many ways, there are some ways to do it, bring a decrease in NOx. For another variable is the air fuel optimization. So there is a way reducing the velocity of the combustion and the density of the combustion. With the combustion density, I mean the amount of energy you put inside the melting chamber. So when there is a high density of combustion, there is a NOx increasing. So a decreasing in that means NOx decreasing. And also, there are structural aspects that affect the NOx formation. For example, the furnace size, because the size of the furnace influence the flame, the shape of the flame and its length. So it's possible this is one of the main aspects of the NOx optimization, the regulation, the optimization of the burners, and also the shape of the flame. And increasing the flame radiation could bring a NOx decrease, because a more luminous flame means it's accompanied by a less temperature, lower temperature, sorry. And so this means NOx decreasing. Also, there are another aspect that are not directly correlated to the combustion, but for example, is the increasing of use of electrical boosting. So part of the energy for the melting is moved from the flames to the electrical share of the energy put inside the furnace, and also could be reduced the NOx formation by some changing in the batch composition. An increase in cullet means a less use of raw material, which means less energy to give for the reaction, and so this we arrive at NOx decreasing. And also there are different type of fuel injection techniques. So for there is this sort of approach for the optimization of the furnace, and we need initially to characterize the setup of the furnace, and at the same time it's important to take into account the energy aspect of the furnace, the emission aspect of the furnace, and it's important to have an energy balance, a thermal balance of the furnace, in order to highlight the main sources of and with all this information, it's possible to optimize the process, and so have the control of the process. And this is not only affect the emission aspect, so the NOx reduction, but also it could help in a way of less energy for the same amount of glass, and have a good quality glass. Okay. So this is a slide who explain this in another way. This is our approach in SSV, Stazione Sperimentale del Vetro. With this technique, this approach, we monitor many aspects of the furnace, in particular the emission aspect, like the flue gas outlet to the atmosphere in the chimney, but also we measure this flue gas in the main, in the most significant point spots of the furnace, like the neck, the port neck, the regenerator chambers, and also the fumes channels. At the same time, temperature and pressure are characterized, and these give a global idea, global context for the furnace, and could help in the process optimization, like I said before, in the process control. These are some of the methods we use for the monitor of the various compounds, pollutant, but also other parameters like temperature and pressure. So, for during combustion optimization, it's important to know what are the parameters, the aspects that could affect the NOx formation. So this graph reports many of the aspects that could affect the NOx formation. For example, in the first one, show how the incidence of the air between air and the fuel could affect the NOx formation, all compared to the rate of the gas, the velocity of the gas. Sorry, the gas, not the glass. And we can see a different, many different way how the NOx formation change. On the other graphs, there is, let me just a moment. Okay. So it's important to set up the burners, and which means to set the air-fuel ratio. You know, when air-fuel ratio get higher, this means more air in the combustion chambers, a better combustion, but this can bring a NOx formation. So it's important to set up this in a best way in order to have the better compromise between glass quality, energy aspect. So don't waste too much energy in the melting, but also in the emissions. But during combustion optimization, there are some process constraints which we have to take into account before progressing to the combustion optimization. It's important to take in account the CO level, carbon monoxide, because it could be harmful for the refractories and regenerators. At the same time, there's not only NOx generated from the furnace, but also there is SOx and others acid compounds. And variation in the redox state of or in the redox atmosphere on the glass melt could affect also the glass color. I mean, for example, is if we are producing flint glass and having too much CO production, CO generation on the glass melt could affect in a bad way the glass color, for example. At the same time, it's important to take into account the thermal profile in the melting tank, which is highly correlated with glass quality. And also there are fuel boosting consumption and the temperature of the waste gas going out from the furnace. So in this approach, this is another slide which try to show how all these aspects are correlated between each other, because the combustion optimization affect the emissions for the NOx point of view. But at the same time, it's important to take into account also the sulfur balance, because the generation of sulfur is influenced by CO level, like I said before. And at the same time, during the optimization, we cannot forget the quality of the glass. So it's important to correlate all these actions to the glass quality. And so, yeah, this is all the things we have to take into account when we are going to optimize the process for the glass furnace. These are our equipment, what we usually do during, for example, this is for also for the emission and the combustion characterization, but also for the thermal balance, where we measure the gas, the flue gas going out from the furnace, but also we measure the temperature of the air and the waste gas in the different spots, like the port neck, regenerators, and the channel. These are the more technical aspect about our strategy from the analytical point of view for the characterization. So, like I said, these are the most significant spot for the emission characterization, and we usually do a grid characterization. So we measure the concentration of the gas in different spots inside the regenerator chambers, because the concentration of the gas, like CO, NOx, SO2, and the oxygen, could change in the different spot of the regenerator. So in order to have a more precise analysis and to reconstruct the constant in a better way, it's important for us to do a characterization like that. You can see in the figure on the bottom left how there is the concentration of oxygen, for example, in the different spot. It's like a grid. Every square is a different oxygen concentration. I forgot to say that, to mention before, that also this type of monitoring, this type of characterization is helpful for example, for CFD, computational fluid dynamics. So with the data we collect, we can compare this data with the CFD simulation and give them a validation with this data. So this is a here there is I want to talk about a small case study in order to explain me better. In this case, we were making a thermal balance for this furnace. In the first plot, as you can see, is a comparison between the specific consumption of a furnace between and the poor rate in the x-axis. And the red point, as you can see, is the specific consumption measured during the thermal balance activity. As you can see, it's quite high compared to the others that are the usual value. We identify that from the measuring of the temperature, there is a high temperature in the regenerator. So, helped by the, helped by the emission characterization, we see that there is a lot of CO in the measured in the regenerators. This means that CO are like unburned fuel, and so the heat is not transferred globally to the melt, to the glass melt, but some of these unburned particles arrive in the regenerators. So we are extracting some energy from the tank, and so this means higher consumption. So there is another problem generated from that. The regenerators are too hot, and also carbon monoxide could affect could damage the inside of the refractories inside the regenerators, but at the same time could affect the quality of the glass. For example, if the glass produces this flint glass, but also the CO have increase the SOx and the HCl concentration in the fumes. So in this case, we proceed for furnace optimization, making another others analyzing and monitoring. So this is the baseline where we have a high concentration of CO at the regenerators, and the NOx was quite low in this case, but like I said, it's important to take into account all the parameters. So then the first step, we reduce the CO concentration. As you can see, it goes from 1800 to 1300, but we were not so happy because we can do it better, something better than this. So as you can see in the last figure, there is the CO average was around 124 ppm, and the NOx was still low. So this is for example, what means a combustion optimization. How we achieve this optimization is, in this case, there is a combination of changing in the air fuel ratio, and and also change in the burner setup, like the corner of the inclination of the burners, the changing the flame shape, etc. These are the improvements we made. As you can see, the three different conditions. So we see a decrease in the CO concentration, a little increasing in the NOx concentration, but still at manageable level. And at the same time, measuring the temperature in the regenerators, we see a lower temperature in that, and so this means a better combustion and also less fuel usage. One other thing that it's important to take into account when there is a combustion optimization is the carryover. With carryover, I mean the phenomenon that where some of particles, dust particles deriving from raw material, could leave the furnace unreacted and arrive in the regenerators, and this could lead to a mechanical corrosion and so damage the refractory. This affects also the life of the furnace itself. So this phenomenon, depends of for example, from the pull rate, the use of different raw material, but also could depend from the how the combustion is conducted, because, for example, high CO levels allow the melting to have more vapor of alkali compounds that could corrode, condensate in the regenerators, and damage them. So this is an example of a measurement we made. As you can see in the first red circle in the condition tree, the small point are the concentration of the compounds potassium oxide, calcium oxide, and sodium oxide. All of them derive from the melting in both a way, or like vapor that then condensate, but also like particles that are carried out from the furnace. In the condition tree, as you can see, we have the highest value for concentration of potassium and sodium oxide, and we registered this value when the pull rate of the furnace was higher. Then we made optimization of the flames. We reduced the velocity of the flame and the shape. We change in some way the shape of the flames, and as you can see, the concentration of these compounds is lower than before. So this is another aspect of combustion optimization, of a primary technique for combustion optimization. Carryover is also useful for with the carryover analysis monitoring. We can build these curves that show how the gas composition at different temperatures. Knowing this could allow us to forecast to where we the major composition of some species. So it's a useful tool for who produce glass, if there are problems in the regenerators of condensation of some material that could affect the life itself of the regenerators. Sorry, okay. Okay. Another thing which is important to do is the sulfur balance. So this is a way in order to find the source, the input for sulfur, and also define the output and how the output are distributed. So, and this is the theory of the furnace, of the sulfur balance. So there is usually 5 inputs that are the sulfur coming from the best, the one coming from the fuel, from the cullet, also internal cullet and foreign cullet, but also the sulfur coming from the filter dust, which is the filter, the dust collected from the filter that could be reused and recycled like raw material. And the furnace output for the sulfur are the sulfate that is going out with the glass, the one that go out of the furnace with the waste gas, and the one with the dust. So this is an example of an experimental sulfur balance we perform. So usually these are the share of how they are redistributed in the input. In this case, we have a furnace that uses electrostatic precipitator dust, which is used and in the furnace for a source of, in this case, sulfur, which is used as refining agent. But also we can see the output, in this case, 48% of going out with the glass, the 47% with the fumes, with the waste gas, and what remains going out with the dust. So another thing I want to point out is in the input, we can see, for example, the foreign cullet, the external cullet, is one of the most critical source of sulfur, because it could it is very variable. It depends of how it is mixed and the amount of colored glass. So for it's important to check this parameter for the sulfur balance. Okay, this is another way to resume the sulfur balance for a furnace. Starting going a little bit faster, because I see that half an hour is passed, so I think I want to go to another aspect of the presentation. Here quickly is the is how we perform, how we made a thermal balance. So there are many input and output to take into account. The heat coming with the gas, the energy coming with the boosting, but also we have to take to check the amount and estimate the amount of cold air infiltration, and we have to verify and estimate also, in this case, the energy going out with the glass. These are all the parameters to take into account when we made a thermal balance. So we measure the flue gas composition, we measure the pressure of the furnace. This is an important aspect because it could give us an idea about the symmetry between, for example, for a regenerated furnace with regenerators, could give an idea about the symmetry between the right flame and the left flame. Also here there are the temperature measure for the flame, for the waste gas, and for the comburant air. Sorry, I see a question. Sorry, I was seeing a question. Yes, Jfan, I think it's possible to share the presentation. Yes, I think. Yeah,
I'm just writing to him.
Okay, sorry. Then after this, I'm going to answer to your question. I'm glad to do it. So, proceeding to the presentation, and we can you can see the in the figure in the bottom also the amount, the estimation of the amount of air leakages into the furnace, because it's something that it's important to check because is cold air entering the furnace, and so this is another source of energy loss. So this is the resume for the furnace, for the energy inputs and outputs. Here is the mass balance of all the flows inside the furnace after a thermal balance, including also the leakages of air inside the furnace. Okay. Okay, this thing, this is a new technique we started to use in the last year. It could be a tool useful in order to optimize the process, because I'm talking about the use of helium like a tracer and inside the furnace. With a filter mass spectrometer detector set for the measurement of helium, it's possible to optimize the process. This technique allows us to determine the infiltration at the regenerators and the reversal valves. It's possible to calibrate the air combustion flow rate, and the more precise knowledge of the combustion flow, the air combustion flow rate could help us in the reduction of NOx, because with a more precise knowledge of the flow of the air, it's possible to regulate better the burners, for example. Also, it's possible to determine the fumes residence time inside in the treatment system, I mean the electrostatic precipitator. So this could help us in the optimization also for the SOx reduction. This is another aspect that could be affected by this technique. And I'm going quick on this. Those are some. Okay. For example, this is a nice example in order to explain how helium works. This is a cross-fired furnace. So we put helium to the right side in the combustive air, and we measure the helium concentration at the fume and the waste gas side of this cross-fired furnace. And in this case, we want to know how the waste gas are redistributed from one side to another. As you can see, for example, in these pictures, we measure that the helium put inside the second port, we find the helium in the first, in the second, in the third port at the waste gas side. And we made this test in all the port in the air side, and we measure the helium in the waste gas side. This is the test, the results of the test, the graph we had. So in the test one, we inject, for example, the helium in the second port in the air phase, and we measure it in the second, in the third, in the first we measure it at the top of the regenerator in waste gas side, the second, in the third, in the one. The second test, we inject the helium in the sixth port, and we measure it in the waste gas side, in the 6th, in the 7th, in the 5th, in the 4th port. The last test was we inject the helium in the 2nd port, but not in the top of the regenerator, but at the bottom. And we measure it at the top of the regenerator in the waste gas phase. And those are the results. This is an interesting test for a crossfire furnace in order to define and investigate the redistribution of the waste gas in the furnace. Okay, I want to cut this part because the time is running out, and I want to talk about this thing that is, I think, more interesting at this point. So there are many aspects also in the last times that regarding the CO2 reduction also, and affect also the glass industry. As you know, the European Union roadmap is to reduce before 2050 the emission of CO2. So there are different approaches in order to reducing the CO2, and there are 4 types, 4 categories: type A, B, C, and D. In the type A, the reduction of the CO2 is direct by increasing the fuel consumption efficiency. So there are different technology. One is the Optimelt type of furnace installed in Netherlands, where there is a steam methane reformer and a oxy-fuel furnace. There is the Craftem system, where it is an auxiliary firing technique for glass melters, and the air liquid ETOX system, where the oxygen is preheated, and the natural gas oxygen and natural gas are preheated at the expense of the flue gas. So it is a way to recover some of the heat from the waste gas. And also there is, this is one of the latest project. It is not already started, but Life Sugar project, where we are involved, like Stazione Sperimentale del Vetro, where there is a reactor, a thermochemical reactor, for the steam reforming of natural gas, using the energy from the flue gas. The furnace which is used is a hybrid regenerative recuperative furnace, which is the Centauro furnace, is a Staraglass technology. Those are the type A way to reducing CO2. Type B is for the reducing of CO2. There is an increasing of the fraction of energy delivered by to the melt by electricity. So there is the FEVE furnace for future project, where the purpose is to reach the 80% of the energy given to the melt with electricity. Type C. In the type C, for the CO reducing, there is a change of the fuel type. Okay, so for example, for the FEVE furnace for future project, the 80% of the energy is given by electricity. The other, the remaining 20%, for example, is given by hydrogen. And another project at the moment are the one made by GWI HVG, based on biogas, or by DNV on a biomethane. Okay. Another type C is the use of burning hydrogen, pure or mixed with natural gas. And then there is a type D. These are not directly affect the combustion, but are on the change of, for example, the batch composition. One of them is the use of pre-calcined raw materials, or non-conventional, like lime, dolomite, or non-conventional raw materials. Another one is the increasing in cullet percentage. And there is something different, which is the carbon capture technology, in order to collect the CO2 in order to give to emit less CO2 in atmosphere. Those are some of the new technology present at the moment. Like I said before, the optimal furnace, the Craftem project. Okay. This is the Centauro furnace made by Stara Glass. It is a hybrid furnace with a regenerative part and a recuperative part. And also have a SNCR technique, which is a non-catalytic, selective non-catalytic reduction for the abatement of NOx, using an aqueous solution of ammonia or urea. And some other aspect or technologies for the NOx reduction, and those are primary technique, is the one studied in the Prime Glass project, maybe something about 2 or 3 years ago. And this project investigates two aspects of the recirculation of the gas. One is the waste gas recirculation. So at the bottom of the regenerators, some share a small part of the flue gas are reintroduced in the air chamber, and so this allow the reduction to 35% of the NOx. And another aspect is the recirculation of air. So this is the hybrid air staging, where some of the combustive air is taken out from the air flow and put inside the waste gas flow. And this is a promising technology, which is already installed in some furnace, from my experience, as I know. And as you can see, these are some of the CFD calculations. So as you can see, this is a primary measure to reduce NOx, where the excess air in the furnace is kept to a minimum value. And so with this minimum volume of excess air in the furnace, we can produce less thermal NOx. There is the problem of the increasing of CO level in the furnace, but this the residual CO that is produced inside the furnace is oxidized at lower temperature in the port neck at the waste gas side by injection of cold or compressed air. As you can see in the figure at the bottom right, as you can see, the left one is the air port, and the right one is the fume waste gas side. So a part of air is taken from the left regenerators, from the left port, and bring inside the right one. And so we have a less NOx formation, and the major CO production we have is oxidized by the share of air which that is taken from the port and put in the other regenerator. This is the same technology, a little evolution of the same technology, which is the high efficiency air staging, which is installed in Castellana Grotte, which is a plant of Vetrerie Meridionali in Italy. Hybrid high efficiency air staging is the primary NOx abatement technology. The system, in fact, connects combustion air and waste gas ports in order to create a combustion staging. The simulation conducted were validated by experimental analysis made by Stazione Sperimentale del Vetro. There is a good mixing with air and waste gas, and this could help in the reduction of CO production and at the same time of NOx production. Okay, the last thing I want to talk about before ending is the Sugar project. It's a life project. Sugar stands for Sustainable Glass Architecture of a Furnace Heat Recovery System, including a steam reformer. This project there are many is a project where Stazione Sperimentale del Vetro is involved with Stara Glass, KT, Kinetics Technology, Johnson Matthey for the catalytic part, Stazione Sperimentale del Vetro for the analytic part, and also the Università di Genova for the research of and the CFD simulation in particular. So the sugar system, the sugar furnace, is a furnace where it's based on the Centauro furnace, where the heat recovery is divided in the refractory and in the metal part. But it is installed a steam reformer unit that transforms part of the combustion system natural gas into a syngas, so CO and hydrogen. So in this way, it's possible to to recover more energy from the waste gas and improve the furnace combustion. Also the efficiency of the furnace itself. The novelty of this application of the steam reformer is that the reaction will not be generated on purpose, but using direct fuel to give the energy for the steam reforming reaction, but it is used by the energy is coming from the recovery of the waste gas energy, the energy that will be lost in the atmosphere. The impacts we expect with this technology is the reduction of gas consumption and also the CO2 emission. And also the NOx will be reduced by the SNCR system already present in the Centauro furnace. Yeah, that's all. Sorry, I start running in the last minutes, but I noticed that I spend a lot of time, so it's done. Thank you for your attention. And if you have any question, I'm here.
That's a very interesting paper, and thank you. And no worries about running over a little bit. The subject was very interesting. While you've been talking, we've had a question from David Moore, and he asks, as we add hydrogen to the fuel mix or completely replace carbon fuels, what are your thoughts on how energy air firing aspects of gas emissions?
Well, about the replace all the carbon fuels with hydrogen. Well, I'm kind of how can I say it? I'm not so sure about hydrogen replacing all the carbon fuels, and because for example, yeah, as I show in the for the sugar project, there is a share of hydrogen which is produced by the waste gas, the heat, the energy coming from the waste gas. But as you know, the hydrogen production with the steam reforming is like making the glass. It has a high energy demanding. So at the same time, we try to recover more energy with this project, but if we think to make hydrogen with steam reforming, for example, we are just moving the energy from burning natural gas to give energy for have steam reforming. So I think we have to find another way to produce hydrogen in order to have it sustainable. I think there are a lot of different technologies that could be used, like electricity in combination with hydrogen. So yeah, this is my idea about that topic.
So certainly in the UK, we are talking about mixing natural gas with hydrogen.
Yeah.
So I think that's probably the crux of David's question is, how is a percentage of hydrogen with methane going to affect the emissions?
Well, the gas emission, I think that using hydrogen, in theory, the NOx emissions could be lowered with using of the hydrogen mixed to NOx, and but I think that I see another question from David Moore. Still need the same abatement technology as at the end of the exhaust. Yeah, I think that something we have to work on about the technology of emission reduction is the secondary reduction system. As you know, the BAT, best available techniques for the glass industry, forecast that they want to low down the limit for NOx, for example, to 500 milligrams on normal meter cube, referred to 8% of oxygen. And at the moment, the only way to reach this value is using, for example, the NOx system, so a selective catalytic reduction. And I think that the way to contain the emission is that one, going with abatement technology. downstream the process.
Mm-hmm.
But I think also that an optimization of the downstream, the upstream activities of the process is still fundamental to have the downstream technologies working better. As you know, an NOx system it's quite expensive, and in order to give him more lifetime, it's important to optimize the process upstream.
Okay, thank you. One more question for myself.
Yeah.
Is I might have missed it in your presentation, but are you able to correlate the waste gas emissions to the level of sulfur that is deposited in the cooler areas of the regenerator?
Yeah, you mean that? Let me.
Yeah, at a certain temperature.
The carryover.
Yeah, the carryover.
Yeah.
Yeah.
Well, I show you some graph where there are. Here we are. Okay. And for this one, for example, those are some theoretical thermodynamic gas composition. So looking at the temperature, we try to estimate the concentration of the species condensated in the regenerators. Can you repeat me your question? Maybe I missed it.
Well, just if there was a correlation between the waste gas emissions to the amount of sulfur.
Yeah, sure, for sure. There is a correlation.
Yeah.
The parameter correlated in this case are the temperature, where you are going to see if there is a condensation of some material, for example, sulfur compounds, the concentration of the sulfur compounds in the gas. So yes, the emission affect the correlated to condensation of sulfur compounds in the regenerators. Yeah.
Okay, we've had another question from Cesar Caloso from Mexico.
Yeah.
And the question is, which is the optimal angle to use in the burners, and how do you estimate? In the presentation, you presented an inclination between 0 to 2 degrees. In our experience, depending on the type of color, our optimal angle of inclination varies between 6 to 8 degrees.
Yeah, thank you for your question, Cesar. So I cannot answer. There is not one single exact answer for this question, because this aspect is affected also by the size of the furnace itself. So if I have a furnace that have a pull rate that can pull 200 tons per day, if is a furnace that can pull, if the pull is 500 tons per day, and there are differences in the shape of the flames, and also these affect the angle to using the burners. So I do not have an optimal angle to give you. For example, in the presentation, you see an inclination between 0 to 2 degrees. And that graph that showed the 0 to 2 degrees was a graph taken from a study made by Stazione Sperimentale del Vetro some years ago. And it was a study made in a pilot furnace. So I do not focus on the absolute values of the inclination, but this is more like an idea of the impact of the degree of the inclination between the burners and the air. Also, yes, it depends of the type of color and the type, the amount of raw material you are using. If you are using more cullet, you can have more flame with a higher velocity. So because there is the less impact of the carryover. There are many aspects. In our experience, is something that we made in the field with the measurement, and we start from what we find at the moment in the plant, and then we start changing the burner, the inclination of the burners, for example, following some principles, but then after this is all about what we see in the field. Yeah, I hope the answer.
Okay, well, thank you, Domenico, yeah, for a very interesting hour, and it's been good with the questions that we've run on longer than we had anticipated. So that's a good indication of the interest in the group for your presentation. So if we can close it down, and again, thank you, and hopefully people will join us again in a month's time when Alan Stevens from Stein will be giving a training course on auditing for hearths. So I look forward to seeing and hearing you all in a month's time. Thank you.